Okay, antiderivatives. So we've talked about definite integrals. Definite integrals use basic antiderivatives, but there's a lot to this. There's a lot of definitions that we're going to need to go over. Okay, so let's start with just the representation of antiderivatives. If capital F is an antiderivative of little f on an interval, then g is an antiderivative of f on an interval I, if and only if g is in the form of g of x equals f of x plus c for all x and I where c is constant. Wow, that's a mouthful, okay? Basically, it's saying that you can represent an entire family of antiderivatives of a function by adding a constant to a known antiderivative, okay? So for instance, knowing that, and they use d subscript x, so it's d in terms of x squared, the derivative is 2x. So you can represent the family of all antiderivatives of that by saying it's g of x equals x squared plus c. So we've kind of talked about this already, but this is the family of antiderivatives. So if you have this function, f of x equals 2x, and you take the antiderivative of 2x is x squared plus c, this function right here, g of x, is the family of solutions. It's all the possible functions that could have 2x as its derivative. So c could be 1, it could be 2, it could be 3, it could be 4, but all of those functions, x squared plus 1, x squared plus 2, x squared plus 3, they all have 2x as its derivative, okay? And c is this constant, and it's what we call the constant of integration, okay? This is going to be really important coming up, okay? That constant of integration. All right. So antiderivatives basically differ by just a plus c. The family of functions represented by g is what we call the general antiderivative, okay? And this function, g of x plus c, is called the general solution, okay? And of a differential equation. A differential equation, and this is what most engineers talk about when they talk about the diff EQ class, differential equations, okay? A differential equation is nothing more than an equation that involves x, y, and the derivative of y, okay? So g prime of x is a derivative. It's the derivative of g. So this is therefore a differential equation, okay? For instance, y prime equals 3x and y prime equals x squared plus 1 are examples of differential equations. They involve x and y and have a derivative in them as well. Okay? That also means if you had, say, dy over dx equals 3x squared plus 1, that is also a differential equation. We've been dealing with differential equations. We've been creating differential equations this entire time. Every time you take the derivative of a function, you are creating a differential equation. That's why it always pains me when I see you guys take derivatives and leave off this part, because what you're doing is you're eliminating the differential equation part. You're finding the derivative, but you're not creating a differential equation. And that's why I got on you guys so much about doing that. Okay? All right. So, finding the general solution of a differential equation, y prime equals 2. We've been doing antiderivatives. Okay, so you need to find the functions whose derivative is 2. Well, this is a pretty easy one. One such function is 2x. 2x is an antiderivative of 2. But there are more than that. Okay, and basically what we've been talking about is that y equals 2x plus c is this general solution for that equation. Okay, again, these words, the terminology is going to become really important. If you don't know what a differential equation is, or if I ask you, hey, find the general solution, and you don't know that definition, you don't even know where to get started. So these definitions are going to become very important. You need to know the terminology. That's what calculus is mainly about. So this is the graph of 2x plus c. Notice that depending on what c equals depends on which one I have. C here is negative 1. C here is 0. C here is 2. Notice all of these functions are parallel to each other. which means they all have the same slope at the same point. The only thing that's different about them is where they actually hit the y-axis. Okay, so they differ by basically their y-intercept. And that's what C is. We've learned that in Algebra 1. When you plug in 0 for x, whatever constant at the end, that is your y-intercept. So going back to the kind of an Algebra 1 idea. All right. Notation for antiderivatives. Okay, so when solving a differential equation in the form of dy over dx equals f of x, remember when I told you it's not convenient to think about that as dy divided by dx? Well, now it is. Okay, it's convenient to write it equivalent differential form. This is what we call differential form. When you have dy, all your y's on one side and all your x's on the other, including the dx. This is what we call a separable differential equation. Okay, there are separable equations and there's non-separable. We'll only be dealing with separable, where we can get all the y's on one side and all the x's on the other. When you get into higher level maths, then you'll start seeing non-separable differential equations, usually in Cal 3 or higher. Okay, but basically what you're going to do, and what I've left off, is that you're going to take the antiderivative or the integral. You're going to integrate both sides. The antiderivative of dy is y. And the integral of f of x dx is capital F of x plus c. Okay? And one of my questions that my kids always ask me is, well, where'd the dx go? Well, the dx is part of this operation. If the dx was not there, we couldn't take the integral. It's actually part of the operation. It'd be like saying, oh, 2 squared is 4. Well, where did this 2 go? That's the operation. You square it and it goes away. So the dx is part of the operation of taking the antiderivative. So this operation of finding all the solutions is called antidifferentiation, or indefinite integration, and is noted by the integral sign. We've talked about definite integrals, so this is now when we're talking about indefinite. Okay? So indefinite integration is basically just finding the antiderivative. Definite integration is using that antiderivative. In both cases, we find the antiderivative. The difference is if it's indefinite, if there are no numbers. If there are no numbers here and here, it's an indefinite integration, and all we're doing is finding that antiderivative. If there are numbers there, then there are numbers that we have to plug in. And then we still find the antiderivative, but then we use it to find the area under the curve. Okay? So there are two types of integration. There's indefinite, which is just finding the antiderivative, and then there's definite, where we find the antiderivative and then we use the antiderivative. Okay? So the other thing is, just like if you have f of x, the derivative is f prime of x, and the derivative of that is f double prime of x. Okay? We now have another antiderivative of f. So going this way is when you take the derivative, and going this way is taking the integral. So if you have integral of f prime, it gives you f of x. If you take the antiderivative of f double prime, you get f prime of x. So if you take the antiderivative of little f, you get capital F. Okay? So this is just notation that you're going to have to remember. Okay? All right. So basic integration rules. So there's this inverse nature. Everything in mathematics, every operation has an inverse to it. Okay? So the integral is the inverse of the derivative. So when you take the derivative and then you integrate it, which is what this is saying, f, capital F prime, you're taking the derivative of f and then you're integrating it, you're basically getting back what you started with because they are inverses of each other. Moreover, that if you take the antiderivative and then you take the derivative, you get what you started with. Okay? They are inverse operations. Okay? That means that some of these derivatives that we've been doing, the only way to find the antiderivative is to know what the derivative is. Okay? So here's a list of the differential rules that we've been going over so far and their integrations. So on this side, you can see this is a constant. When you take the derivative of a constant, you get 0. Well, when you integrate 0, that means you get a constant because they are inverses. Okay? This is the power rule that we learned. This is what we call the anti-power rule. So in the power rule, we move the power out front and we subtract 1 from the power. Inverse means doing the opposite operation in the opposite order. So here we multiplied first the power and then subtracted 1 second. So in the antiderivative, we add 1 to the power first and then divide by the new power. So for instance, if I'm taking the integral of 7x squared, this is saying take the antiderivative of 7x squared. So we're not going to worry. The constant multiple rule says I don't have to worry about the 7. So I just take x, add 1 to the power, and divide by the new power. And then I can't forget my plus c. Okay? Basically, you need to think about that plus c as plus credit. If there is no plus c on an indefinite integral, it is wrong. Okay? But when we get down here, say into the trig formulas, the only way that you know the antiderivative of cosine x is sine x is that you know that the derivative of sine x is cosine x. It's kind of like roots. How do you know that the square root of 16 is 4? Do you even know how to take a square root? What operation exactly is a square root? What do you do to find the square root? Divide by what? But you don't know the number. That's what you're trying to find. So you're defining the root based on the fact that you know 4 squared is 16. Therefore, its inverse, which is the square root. The square root of 16 is 4. You're defining a function's inverse by the function itself. And that's basically how the integral works as well. Some of them, the only way you're going to know what the antiderivative is if you know the derivative. Okay, so if you've forgotten any of these rules, which I know you probably have, you need to go back and look them over. Okay? And again, this should look familiar. These are the 4 steps. We have our original integral. We rewrite, we integrate, and we simplify. It's the same steps we use for the derivative, where it said original derivative, rewrite, differentiate, and simplify. But now we're doing it with integration. Okay? So we've seen how that y equals f of x dx has many solutions, each differing by a constant. Okay? That means graphs of any 2 derivatives of f are vertical translations of each other. Or basically, they differ by their constant. So this is giving you an idea of this idea of a general solution differing by a constant. Depending on what c is, every one of these cubics is a possible solution. Think of it kind of like, we also call the general solution the family of solutions. Okay? So think of it like if there's a phone call at your house and they ask for somebody with your last name, Mr. or Mrs., and they use your last name. Do you know exactly who they're talking about? No. you need more information. You need a first name to go with that to figure out which person in your family it's exactly talking about. And this is the same way. This general solution here has many family members. We need another piece of information to be able to figure out which one of these is the correct member we're looking for. And that's something we've already done. It's called the particular solution and initial condition. Okay? We've been doing it with velocity, position, and acceleration. If I gave you the velocity equation, you found the family of solutions for position, and then I gave you that initial condition to allow you to find that particular solution. Okay? So again, using that idea, this is the general solution. So if I have a derivative, 3x squared minus 1, we find the antiderivative, which is this. This is the general solution. But then I gave you this initial condition. I said, well, wait a minute. When you plug in 2 for x, that should be equal to 4. And then we use that initial condition to actually solve my general solution for the particular. So this is what we've been doing with velocity and position. So you plug in your 2, you set it equal to 4, you find that c is equal to negative 2, and so this right here is my particular solution. Okay? We've been doing this, you just didn't know that it had a certain name to it. Okay? And again, I could ask you the same thing. When I ask you to find position when x is 2 and your position is 12, it's just the same thing as me saying, hey, find the particular solution for this. Okay? So there's a bunch of different ways of asking the same question.